Hello again and welcome to our last video for the while on Excel and processing your data for biology. In this video we're going to look at continuous data, and if you go back to the first video on continuous data, so continuous data part A, you will remember that I had a scenario where we looked at the effect of temperature on the concentration of dissolved oxygen, temperature measured in degrees centigrade, dissolved oxygen in milligrams per liter. Both of these are continuous data, and when we have got two sets of continuous data, we should be looking at choosing a scatter plot. Now, this is not the same as doing a plot of the averages and joining the lines up. That's what I like to call a dot to dot. We don't do a dot to dot, we want a scatter plot. So I advise that you set up your data tables, your data collection tables, so that you have got all your conditions down one column, and your repeats are just a repeat of the same condition, because this will help Excel to plot your scatter plot. And you put in all your results, so your dependent variable, they go down in the other column. It's super simple. You don't need to find an average. You don't need to do anything else. You can go straight to plotting the scatter plot. So let's get on with that. So in this case, we're not going to go to the data tool pack just yet. We might go there in a little while, but not just yet. We're going to go straight to drawing our graph. So we're going to go insert, our chart, recommended chart. We want to pop down here, and you can see that we can insert a scatter plot or a bubble chart. I'm not interested in anything but a scatter plot. We're trying to keep it neat, we're trying to keep it simple. And this is the scatter plot that we want to choose. So we're going to choose that one. But before we choose that one, we actually need to highlight our columns. So let's do that now. We're going to highlight both columns. So you've got all the data that you want to enter into your scatter plot. Don't forget, it has to be numbers only. No units or letters or descriptions. We go to there, we go to there, and here we have our little scatter plot. First thing you're going to do, remember, take out the chart title, because real scientists don't have a chart title. They have a figure description. And that figure description will be the same as your table, because your chart is just plotting exactly the same as what's in your table. So you can happily just copy that and you can paste it underneath, and all you have to do is change table to figure. And now you have a perfectly good heading for your graph. In the graph that I've got here, you can see that the scatter plot is happening up here on the top right hand corner. We could neaten this up to make it bigger, or so that we're not going down to 0. I'm not going to, so that it just looks bigger and neater. But you know what? There's actually no extra marks in that. So I'm very happy with the scatter plot just as is. If you want to make it prettier, you go for it. There are a few things missing though. We're not going to get full marks for this section with just a heading. We need to have our axes labels, so let's add those. These, remember, you're going to click on the first aid sign. That's what I call it, because it's where I get all my help from. I've got axes, I want axes titles, so I click there, and I can actually copy these from here. I've got water temperature in degrees centigrade. That is my x-axis. Put that in there. And I have got concentration of dissolved oxygen over there. And I can pop that in there. Now this one needs to be adjusted. Remember, I told you that we don't want to have dodgy superscripts. So let's fix that. In case you've forgotten, you're going to go superscript and that puts it into degrees centigrade instead of into 0 centigrade. Just to make sure that you're doing your best in terms of communication. There we go, all fixed. So here we've got our scatter plot. I'm going to make it a bit bigger. You can see what's happening. Okay, now you don't even have to do a line of best fit. You could just interpret your data as is, straight from your scatter plot. But let's put in a line of best fit. Now, line of best fit is often called a regression line. I'm going to pop that up here just in case you forget, because it's one of those things like a regression line. What is that? I took ages to remember that a regression line is really just the same as a line of best fit. At least it is in biology. I'm sure it's probably different in statistics. But let's go. Line of best fit, regression line. Just to help you remember. Make it easy. Alright, so to do that, we're going to go down to trend line. Okay, now we're not just going to fit any old trend line. So let's go to the arrow here. You need to think about what kind of trend line you should be getting. In the research for my rationale for this particular investigation, I discovered that as the temperature increases, the level of dissolved oxygen decreases. And I'm pretty sure that over this range of temperature, it's going to be almost a linear decrease. So in this case, I can go for a linear one, but let's have a look at what the options are, because often you're not going to have a linear line of best fit. If you think about, for instance, enzyme reaction rates with temperature, that's not going to give you a linear line of best fit. So you've got to think, you've got to do the thinking for the Excel. So we've got a choice here. We've got exponential. That's not going to work. Linear is definitely going to work in this case. Logarithmic, polynomial. Okay, but we're going to go linear. And I'm only going to put it between the first and the last points, because actually I have no information about what the dissolved oxygen levels are below 18 degrees. So I can extrapolate in my theory, but I've got no information, so I'm not going to plot it all the way up there and all the way down there. I also think that it's important to have an equation. An equation helps you to talk about the data in your data interpretation. So I'm going to click on display equation on the chart. And I'm also going to display an R² value on the chart, and we'll talk a little bit about that later. So I'm going to click on that and I'm done. Move that out the way. Now I don't want all of this cluttering up here, so I'm going to just move that over to there. I've got my equation. My equation says y equals negative. If the one increases, the other decreases, sloping down to the right. Okay, and the R² value tells me what the probability is that any point on this line is going to be on the line. Our R² value here is 0.65, which means that 65% of the dissolved oxygen concentration is determined by water temperature. That's not a very high amount. You need to be careful how you word. You'll notice how carefully I worded that. I didn't say that the closer the R² value is to 1, the more reliable the data is, because that is not true. Okay, so you can say 65% of your dependent variable is explained by your independent variable. And that's it. We've done our graph. I think the easiest way to calculate the range is just to do it manually using Excel. Don't forget that you have to show how you've processed your data. So if you do decide to use the range, you need to say how you've done it. in Excel or by hand. But I'm going to just add a column here and call it the range. And I'm going to calculate the range for each set of different conditions. So over here, I'm going to say equals, because equals tells Excel that it needs to do a calculation. The range is the largest number minus the smallest number. So if I look over here and find the largest number is 6.1, and I'm going to subtract the smallest number, which was 5.5. Press enter, and I have a range of 0.6. I'm going to just do the same for 20. There are quicker ways to do it, but this one is just really straightforward. So the largest number was 5.9, and I'm going to take away, oh no, the largest number was 6, and I'm going to minus 5.8, which is a range of 0.2. Double check, yes. Now it's always a good idea to keep checking that your answers are reasonable. So if we have a look over here, we've got a range of 0.6, and over here a range of 0.2. That indicates that there's a larger spread of data for the different repeats at 18 degrees centigrade than there is at 20 degrees centigrade. Let's check our graph. If we look at our graph, we can just see, looking at the spread of the dots, because that's pretty much what it is, this is the range. There's a bigger spread of our scattered plotted dots at 18 degrees centigrade than there is at 20 degrees centigrade. So it's a quick check to make sure that we're not making an error. I'm going to quickly do the last two. And I've calculated the range for each different condition. Now, something that's important to remember that a lot of people get wrong, and I see it's wrong on a lot of graphs that I Google, is putting error bars on a scatter plot. You don't put error bars on a scatter plot. A scatter plot is every piece of data plotted onto your graph. So there's no place for error bars. Should be no error bars. Now, talking about the range is much easier than discussing the R-squared value. But before we talk about the range, let's discuss a little bit how we are going to talk about these data. You know that you need to interpret the data, but you also have to analyze the data. So there are two things that you need to do: interpret and analyze. Interpret means say what the data is saying. And when we interpret data, we need to do two things. We need to interpret the data biologically, and we need to interpret the data statistically. So it's easiest to do the biological interpretation or the scientific interpretation. Basically, what that is asking is, what do these numbers tell you about the water temperature and its effect on the concentration of dissolved oxygen? You're going to say that as the water temperature increases from 18 degrees centigrade to 24 degrees centigrade, the amount of dissolved oxygen decreases, and you need to give it a number. So reading off my graph here, I've got from 6 milligrams per liter to 5.3 milligrams per liter. Another way that you could do it is you could find the average for each set of data, as long as there are no numbers that look like they might be outliers, and use that average instead of just reading it off your graph. That's up to you. But on this graph, I can see quite easily, and I have described that trend. Now, I can also say that it decreased steadily because this is a straight line decrease, we've got a gradient of negative 0.12. So we know that it is a decreasing in a linear manner. So you can include that if you wish. And that would be your biological interpretation. I'm going to take a minute to just pop it in here. You also want to do a statistical interpretation. So you might want to talk about the R-squared value being 0.64 or 0.65 when we round it off, which means that 65% of the data about dissolved oxygen is explained by the change in water temperature, which is not tremendously significant. Or you could discuss the range. So when we've got numbers that are this small, a range of 0.6 is quite a large range. So you add that as well. Okay, so I've done a bit of an interpretation here. Here's my biological interpretation of the data. Here's my statistical interpretation of the data. So I've said the R-squared value is 0.65, thus 65% of the change in dissolved oxygen is explained by the change in water temperature, which is a relatively low value, indicating that these results are not very significant. The range indicates that the data for the samples taken at 18 and 24 degrees centigrade had the highest spread, thus indicating that these data might be less reliable. Now, it's really important that you have a look at your raw data, which is why I like my students to include the raw data in their report, because it's the raw data where you can see whether there are any numbers that need to be considered. They might, something might have gone wrong in your experiment procedure. And remember that you have to evaluate the reliability of your data, not the reliability of your method. If I run my eye down these data, I can't actually see anything that stands out as terribly different. Those numbers are all fairly close, so there's nothing that really stands out for me now. But in doing the test, I might have noticed that perhaps one of my samples had been done last or had been done later than all the other samples, and there might be some reason in the method that has caused this R-squared value to be slightly on the low side. So that's about it for now. The next section, it doesn't involve using Excel, it just involves evaluating your data and your methodology and making suggestions for improvements. Hopefully I'll be able to get that video out soon. Thanks for watching. Hope that was helpful.